Quantum superdense coding is a really fun demonstration of quantum machines, and it introduces a lot of key concepts of quantum computing. Here, I'll cover what quantum superdense coding is and actually take you through the steps of doing this on the online IBM Quantum Experience program and how to write it in OpenQASM. So before we start, make sure to hit the like button and subscribe if you're new here for more videos on quantum computing, tech, and coding. So first, let's start with what is quantum superdense coding? Quantum superdense coding actually moves two classical bits of information using just one qubit. So you may ask, how is this different from quantum teleportation? Well, it's actually almost the opposite. What quantum teleportation does is it actually moves one quantum state to another qubit, and that actually uses classical bits to do that. But of course, it uses some of the same concepts and some of the same gates that you'll see in all quantum algorithms. So if you want to learn more about that, check out this quantum teleportation tutorial that I made here already. So first, let's talk about qubits and superposition and entanglement. So as I mentioned before, quantum superdense coding is a protocol to transmit two classical bits of information using one qubit. And this one qubit can exist in a superposition of a state of 0 and 1. And that state, what it tells us, is the probability of that qubit collapsing into the 0 or the 1 state, which means we can set it up to say it collapses 50% chance into state 0 and 50% chance into state 1. So instead of writing 0 and 1, just the numbers, we actually use what we call Dirac notation, and this represents a vector. So the 0 state, as represented here with Dirac notation, is just a vector, and it looks like this, 1, 0. But we also have the 1 state, which is the excited state, and that vector is 0, 1. So the key difference between classical bits and quantum bits is that these quantum bits can be in a superposition of the state. Superposition of the state 0 and 1. But what does that actually mean? How can you be in a superposition? Well, let's look at an atom with different excited atomic levels. So what we can do is we can actually take the electron and excite it from the ground state to an excited state. So what happens next? That electron can actually release energy, and that releases a photon, and it can go down to one of the ground states. So if we're looking at this atomic structure actually, you can see there's two kind of mid-level states, right, that are about the same energy level. So when the electron can collapse, it can go into either one of those with about a 50% probability. So this is how we say that that electron can actually be in a superposition. We can't actually control which of these two levels it'll go into, but we do know that there's some probability it'll go to one or the other. So while this is a simple example of what a physical implementation can actually look like, there's a lot of other hardware implementation of qubits, including photons, trapped ions, and even synthetic man-made qubits, like Josephson junctions. So now let's say we have our favorite crypto team, Alice and Bob, and they're kind of worried that quantum computing may break RSA encryption, so they want to start sending their data using quantum states instead. So the protocol starts out with a shared entangled state between Alice and Bob. Then we can actually encode one of 4 different messages using different gate rotations on that qubit. So let's go ahead and actually set up our quantum program and do this. So first we set up the classical and the quantum register, 2 classical bits and 2 quantum bits. While we use 2 quantum bits in the program, we'll send only one of them. So first we need to actually do the superposition and entanglement before we apply the gates to encode the classical message that we want. We start with the initial state of 2 qubits in the ground state, and we apply a Hadamard gate to qubit 0 and the CNOT gate to entangle qubits 0 and 1. So a Hadamard gate is one of the key pieces of information in quantum information science. You apply the Hadamard gate to a qubit to put it in equal superposition, so 50% chance of collapsing into state 0 and 50% chance of collapsing into state 1. So we go ahead and add the H gate. The next step is entangling the 2 qubits using the CNOT gate. The CNOT gate, which stands for controlled NOT gate, can be used to entangle and disentangle qubits. The CNOT gate flips the second qubit, the target qubit, if and only if the first qubit, or the control qubit, is in the 1 state. What this means is that the state of the target qubit cannot be described without the state of the first, meaning that the outcome is going to be correlated. So let's put the CNOT gate in. Then the next step is to apply gate to the first qubit, depending on the message that we actually want to send. For the first gate to encode a 0, 0, we apply I, the identity gate, which doesn't change anything about our initial state. You see, the resulting state is the same as our original entangled state. For a message 0, 1 that we want to send, Alice can apply the poly X. So this is a rotation around the Z-axis. You can see, taking your right hand, the original shared state would spin to the back of the Bloch sphere. In the same way, you can apply the Z gate to encode the message 0, 1, and then XZ to encode 1, 1. So these states are very important. They're called Bell states or EPR pairs. This is another key concept in quantum information science, and it tells us how measurements are correlated. So let's go ahead and do that on the quantum computer and encode 1, 1. We encode it on qubit 0 and apply the X and the Z gates. It doesn't matter what order we do this in, the Z first, the X, because Pauli matrices are Hermitian and unitary, and you get the same answer even if you flip them. So then we send that qubit 0 over to Bob, and now we need to decode the original message. To decode, we apply the C0 gate to both qubits and then the Hadamard gate to the first one, and then we measure. Remember, you can also execute this on the IBM Quantum Experience. So then we can choose our backend here, and you can see you can choose different ones and choose the number of shots or attempts. Remember, this may take a bit of time depending on the amount of people who are in front of you in line to use these quantum chips. And remember, there's going to be some experimental noise when you run this on a real quantum computer, because what happens is the system decoheres or it loses information. This can happen because quantum states are really fragile and they need to remain untouched until we measure them. But a measurement can really be anything. Anything as simple as an atom bumping into another atom can decohere the system. And in these superconducting chips, like the IBM system, they're held at really, really low temperatures to reduce the amount of noise. But there's still going to be some. So congratulations here, you've completed the quantum superdense protocol and actually sent 2 classical bits using 1 qubit. Now, I would strongly recommend here actually doing the math here and seeing what happens when you transfer this information. If you look at my quantum teleportation video, I went through the math a little bit there, so go ahead and do that matrix math here as well, and apply the gates to the quantum states. Doing these exercises and the math will help you really understand the basic building blocks of quantum computing. And of course, if you want even more practice, remember to subscribe to this channel for more videos.